Sorry for the delay, but now it's really time for Ignacy from WebInterpret to tell us something about how to write code that's easy to change. Welcome, Ignacy.
Yeah, I'll be talking about solid principles in Python. Solid principles help you write good and clean code. But why do we write bad code? There are many reasons for writing bad code, but I think that the following ones are most common. Usually we write bad code just because we don't know how to write better one. We try to write best software we can. And if we only knew how to do that better, of course we would, right? But sometimes we know how to do it better, and still we don't. And that's when we are in a hurry. When we have deadlines, when a change is crucial, and we need to finish it as soon as possible. When there's a critical bug and we want to fix it quickly. Then we say to ourselves and to our colleagues that it's just a temporary solution, and we promise to refactor it later. We even put a to-do comment about the code about consciously. But of course we never refactor it later, because we don't have time for it. We have other deadlines, we have other critical bugs, and refactoring would take just too long. And that's how our software rots, littered with temporary workarounds to do and fix comments. We also write bad code even if a change is not so urgent, but it influences other parts of the code. So it would again require a huge refactoring for which you don't have time, or it would simply be too hard. And that's why we don't like changes. I call it the fear of change. We'd love to be able to design our applications up front before we even start the implementation. We love to predict all the use cases, all the corner cases, all the optimizations, to design our application so that it never changes, so that we don't have to ever touch it again. And thus we're mad when someone comes to us and tells us that the requirements changed after we've implemented something. And tells us that the requirements change, we have to rewrite the code, lots of code that we've spent time on. And usually we've refactored lots of code around before, but it changes for the previous requirements. And they tell us to be agile. Most of us work in Scrum or Kanban, so they want us every day to report what we've done. They want us to estimate our work, we measure the velocity, so they want to control us, right? That's what some developers think about Agile. But Agile is not a business thing. It's not a tool for managers to control developers. Agile was introduced by developers to make the developers' work easier. It's directed to developers in the first place, but also to business and clients. So Agile helps developers to cooperate with management and clients. One of the 12 principles of Agile Manifesto says to welcome changing requirements. The creators of Agile have realized that requirements change, and they change pretty often, and we can't do anything to prevent it. So we should accept the fact of changing requirements and be prepared for changes. That's why we have these daily meetings and short iterations with sprint reviews at the end. So we show our latest changes to the client as early as possible, so that we could react to the feedback quickly. And not only the client's feedback, but also our own observations. Because we often realize during development that something could be done better, or that we should change our priorities for the upcoming sprint. So thanks to continuous feedback, we can react to changing requirements quickly before it's too late. But there's more in this principle. It says, welcome changing requirements even late in development. So even if requirements change long after implementation, we should be able to adapt to these changes quickly. And how should we do that? How to write software which is easy to change even late in development? Solid principles will help you. Solid is an acronym for 5 basic principles of object-oriented programming. Those principles were collected in early 2000s by Robert Martin, also known as Uncle Bob, who's one of the authors of the Agile Manifesto. Solid is actually an acronym of acronyms, because every principle has its own acronym. So we have SRP for Single Responsibility Principle, OCP for OpenClose Principle, LSP for List of Substitution Principle, ISP for Interface Segregation Principle, and EIP for Dependency Inversion Principle. The goal of Solid is to make software easy to understand, easy to maintain, easy to extend, unit test, and reuse in different contexts. It's all about ease of change and about loose coupling. Because the problem of software which is hard to change is that its components, its different parts of the system are too tightly coupled. And even if you'd like to change one small thing, one small detail, you still have to change lots of code, all the parts of code that are related, that are tightly coupled to the code that you want to change. But before I even heard about Solid, I heard about this principle called separation of concerns. We all know this principle. In Python and other languages, we have MVC frameworks for web applications or desktop GUIs. So our application structure is separated into 3 layers. Model, where we model our database. View, which is a presentation layer. Now, web application, it would be, for example, HTML templates. There's no business logic in it. It just represents our data in a visual form. And controller, in this layer, we accept a request from the client and we return a response. The goal of this separation is to separate concerns in our applications. For example, if you'd like to change the layout of our website, we change only the view layer, and other layers stay untouched. It often happens that developers implement business logic inside controllers or models, and I did the same, until I observed that when my business logic is too tightly coupled to a framework or web or database, it's hard to unit test it and to reuse it in different environments. For example, if I had to add a console script that does something similar to a controller, I didn't want to prepare a fake HTTP request in my script, right? I wanted it to be independent of the environment. So apart from the model, view, and controller, there's another layer. It's business logic. So now controllers only accept an HTTP request, for example, get some data from it, like get or post data, and pass it to a business layer. And all the logic happens in the business layer, and finally the control goes back to the controller, where an HTTP response is prepared and returned. The business logic doesn't know whether it will be invoked in a web environment, desktop GUI, or a console script. So I started writing those classes that are called services, which implemented logic related to each service of my application. Unfortunately, they were so-called gap classes with far too many methods and responsibilities. I felt that something's wrong about them, as it was hard to maintain such huge objects. But at least I have separated business logic from the web. That was already something. Then I started splitting these monsters into smaller classes and smaller functions, and it appeared to solve lots of my problems. Then I read the Clean Code book by Uncle Bob, and I finally found out that I'm not alone with all my thoughts and feelings about object-oriented design. And in this book, I read about the first principles of it, the single responsibility principle. This principle states that every class should have only one responsibility. In Python, where functions don't have to be defined inside classes, it also applies to functions. So, what does it mean to have only one responsibility? It doesn't mean to do only one thing, you always do more. So say you have a function for sending email reports, like in this example. It gets data for the report, it formats the data, and finally sends the report via email. So it does 3 different things. But if each of these things is implemented in a separate function, and the main function just calls them, then it's not responsible for how they are implemented. It doesn't have to know how to get the data. It doesn't know how to format the report. It just tells these functions to do their job. The function for sending email reports is responsible for only one level of abstraction. In order to send a report, you need to perform 3 tasks. You have to get the data, format the report, and send it via email. So here, just sending email report is the highest level of abstraction, and we perform 3 tasks on the lower level of abstraction. Each of these 3 tasks need to perform several different tasks on an even lower level. To get the report data, we need to build an SQL query, send the query to a database, and parse the results on data objects. To send the email, we need to build an email message, connect to an SMTP server, and send the message. Uncle Bob defines responsibility as a reason to change. So a class should have no more than one reason to change. If you'd like to change the way reports are formatted, we should not need to change the class responsible for preparing report data. If you'd like to change the database for articles, we should not need to change the controller, because the controller is not responsible for database. Okay, so let's summarize the advantages of the single responsibility principle. First, it's readability. If you have a method with like 10 or 20 lines of code, each responsible for a different thing, you have to scan through all the detail before you reach to the code that you're currently interested in. On the other hand, if you had a separate class just for formatting the report, then formatting is separated from the rest of the code. It is abstracted from the context in which it is used. You focus on one responsibility at once. You're not distracted by the surrounding code. Also, you name the responsibility. You have a class called report formatter, and you know what it does, right? By its name. You see the name and you know what's inside of it. You don't even have to read the code. Reusability. If you have a separate class for sending emails, you can use it to send any kinds of emails, not only report emails, but also newsletter, registration emails, and finally, entities with only one responsibility are a lot easier to test in isolation. Let's take again this function with 10 lines of code. It's responsible for a different thing. To test everything, you need to write a set of tests for each line, or a couple of lines. So you can end up with like 30, 40 tests for the same function. Even though you want to test just one part of the function, like formatting report, your test still has to execute the whole body. It has to get the data from database, it has to send the email. And it's hard to extract a particular variable that you want to assert in your test. and it takes time to execute the whole byte in every test. Of course, you could monkey patch all the code that you don't want to execute, but it requires you a lot of monkey patching. All your tests will have similar set of mocks, for example, for mocking our database, and the tests will be unnecessarily too long and complex. Hence, it's better to have readable tests than readable code. Now, if you'd like to change just one thing in this function, you need to change all the mocks for all the tests. Testing then becomes painful. You don't write sufficient amount of tests simply because it's too much overhead. And every change in code requires you to change lots of different unrelated tests. On the other hand, if different responsibilities are separated into smaller functions, it's a lot easier to unit test. It has only one part of code at once. You don't need to monkey patch. You have small input, and you get the output directly from the function, so you can assert it. Now, let's see how easy it is to make changes. Previously, we formatted reports to HTML documents. Now requirements change, and we want to format reports to PDF instead. What code do we change then? We don't have to change the code responsible for preparing report data, nor the code responsible for sending emails. We don't even have to change the function for sending email reports. We change only the function for formatting reports, only the function that's responsible for the change. But now we have another problem. The requirements changed again, and this time it will not be so easy to apply the changes. Now we need to be able to send reports sometimes in HTML and sometimes in PDF. If you have two different report formats, you need two different formatting functions. One will be called format HTML report, and the other one will be format PDF report. So far, everything's okay. But formatting is not everything we need. We need to be able to send two kinds of reports. And the only way to do that would be to copy the old function for sending email reports to a new function and call the second formatting function, the one for formatting PDF. Is that okay? It's not, of course, because we duplicate code. We repeat ourselves. We have the only difference between these two functions is one dependency. And you have to write unit tests for both of these functions, the same unit tests. So we repeat ourselves again, and repeat the tests. And there are better ways than that. And here comes another solid principle, OpenClose Principle, which states that software entities, like classes, modules, and functions, should be open for extension, but closed for modification. What does it mean? Let's look at the example. The only way to extend our function is to use a different formatting function. The only way to extend our function to use a different formatting function is to modify the function's code. It means that the function is closed for extension and automatically becomes open for modification. So the only way to extend it is to modify it. So rather than writing a new function from scratch, which differs from an existing one by only a small detail, we should be able to extend the existing function. You know this acronym TRY, it means don't repeat yourself. As our function was closed for extension, we were forced to break this rule and repeat ourselves in two different places. So how could we open our code for extension? One way would be to move our functions to methods of a class, because classes can be easily extended by inheritance. So we have each responsibility implemented in a separate method, one for preparing report, another one for formatting, and another one for sending email. If we'd like to change the way of formatting reports, we would create a subclass which would override only the method for formatting. So we can extend this class by inheritance. We don't repeat ourselves, but still it's not the best way to go. Because there are other problems here. We've lost the single responsibility. The class is no longer responsible for 3 different things. And we've lost reusability. Of course, we can use this class to send any kinds of emails, not only report emails. But should we use a class called email reporter to send registration emails or newsletters? Should a class used for sending emails carry the whole baggage of other methods for reporting? What if we'd like to extract the mechanism for sending emails to a separate library or some other project which doesn't use reporting? Our code is no longer portable. We've lost portability. At first, I tried to open my code for extension like this. I had each responsibility in a separate class, and the dependencies, the dependent classes, were created in private methods, instances. Here we have report formatting, extracted to an HTML report formatter class, and we create its instance in a private method, later call its public method. It's better than the previous example because now each class has its own responsibility, each class is reusable and portable. We can also extend it by inheritance, where we change only the method for creating the dependency. But it's still not responsible for formatting. It just creates the dependency. But still it's not perfect. I think that inheritance is just too complex. You have some methods in one class, other methods in its base class, and yet others in the super class. And it's even worse when mixins get involved. And you have to write new classes just to override one method. Your tests have to make sure that it still works with the methods from its base class. So I think that inheritance is really unnecessary, and there are better ways than that. Let's get back to our old function and wonder, what's the problem here? Why is it closed for extension? The problem here are the dependencies and the fact that they are hard-coded. This function explicitly says which exact function to use for formatting the report, and there is no way to tell this function to use other formatting function. And here's a solid principle which tells us how to solve this problem. The dependency inversion principle inverts the way we define dependencies. It says that instead of defining them inside functions or methods, we should be able to set them from outside. To set dependencies from outside, we could use dependency injection. We would add an argument for each dependency. One for the function for preparing a report, one for the function for formatting, and the other one for sending email. Now our function doesn't know what function it will use for formatting a report. Instead of importing a concrete function, it asks for the functions. But it's not an elegant solution. First, our functions interface gets polluted. Then we have input data mixed with dependencies. And without looking at the body, it's hard to tell which argument is used for what. It requires us to pass all the dependencies at runtime. Every time we want to send an email report, we have to pass all the dependencies. And all of them will be passed between different functions. So if we have a function which calls send email report, it will also have to accept dependencies for preparing a report, formatting it, and sending email. This example shows how it would look like if all our dependencies would have their own dependencies. So prepare report needs find offers function to find offers for the report. Format report needs Jinja environment and template name, because it formats report to HTML using Jinja templating engine. And send email needs SMTP address and sender address. So we end up with tons of arguments about which the function should not even know. The function is unreadable and it's so hard to use it. And here's how dependency injection looks like in classes. The method of this class looks almost the same as our function before we started injecting dependencies. It has the same two arguments, email and time period. We have the same logic, also 3 lines of code for each step of procedure. The difference is that instead of calling functions, we call methods of other classes. While in function we have to pass the dependencies into it, next to the input arguments. In classes, we can leave the interface clean and pass the dependencies to other place, to the initializer. Now we have input arguments separated from the dependencies. How do we inject those dependencies? Here's how you do that. You have 2 different kinds of reporters. One sending HTML reports, and the other one sending PDF reports. We share the same dependencies for preparing reports and for sending emails, but they use different report formatters. Notice that we don't have to pass classes, but we pass instances. We can instantiate an email sender once during the whole lifetime of our application. And we use this instance to send emails in many different places. You don't have to create new instances every time you want to use it. Create it just once. And below is how you use the reporters. Even though they use different report formatters, you still call them the same way. You don't have to pass the dependencies on every call. You're already injected into them. And here's an example of dependencies with dependencies. So the report preparator needs an offers finder, which needs a database connection. So we simply create an instance of each dependency and we pass them where they needed. And here we pass the report preparator from the previous slide to the email reporter. The email reporter doesn't have to know about the dependency for report preparator nor the report formatter. Thanks to that, we can pass 2 different report formatters even if they don't share the same dependencies. We couldn't do that with functions, and that's because email reporter does not depend on concrete report formatter, but on its public interface. The dependency inversion principle says dependable abstractions do not depend on concretions. So you should not know what class you will use, but you should know its public interface. You should be able to use any class which implements a certain interface. So what is this interface? In languages like Java, we have explicit interfaces. Something like a class, but without implementation, like a template for a class. Here we have an interface for report formatters, which defines that all the formatters need to have a public format method, which accepts a report and returns a string. When we want to implement a concrete formatter, it has to follow this interface and explicitly say which interface it implements. Then, in a class that uses the report formatter, we explicitly say that we want a class that implements the iReport formatter interface. We don't say that we want the HTML report formatter, but anything that implements the interface. In Python, we don't have to write interfaces, but we depend on them. Every class and every function implicitly implements certain interface. An interface of every class in Python includes public method names and their arguments. Here it would be method 1 and method 3, but not method 2 because it's private. Nobody should depend on it. Type of return values. So when calling method 1, we should expect a list. When calling method 3, we should expect an integer. And public attributes. From outside of this class, we can use the second attribute, but not the first one, because it's private. So every class that has public method called method1 with 2 arguments, method3 with 1 argument, and attribute called attribute2 will implement the same interface as the class on the slide. Notice that an interface does not include the initializer. You can have 2 classes with the same interface but different initializer. Like these 2 classes. Here we have 2 different report formatters. The first one, Jinja template report formatter, has 2 dependencies injected into the initializer. And the second one doesn't have an initializer at all, doesn't need any dependencies. But both of them have format method with report arguments, so both of them can be used in our email reporter. Both of them implement the same interface. The email reporter accepts an instance of a report formatter. It doesn't have to know the type of the formatter. It doesn't even have to know how to initialize it. It only requires the formatter to have a public format method which accepts a report report argument and returns report body. Many times I've seen in Python injecting classes as dependencies, like in this example. If you do this, you make your code harder to extend because you depend on the initializer. Here's again the example of dependency injection in function. Here you have 2 functions for formatting report, the first one for HTML, the second one for Markdown, and the first one has 2 dependencies. And we could not use the Markdown report formatter in the send email report function because it does not need the Jinja environment nor template name, which are injected into it. So this function is still closed for extension. I'm going to skip this slide because I think I don't have time. Okay, let's get back to wiring dependencies together. Where should we do that? We should create our reusable instances along with their dependencies in one place, at the highest level, nearest the main entry point of our application. This way, we separate implementation from coupling, as in the separation of concerns. If we want to change the implementation, we alter the code of the class. But if we want to exchange a dependency or change configuration of an object, we alter the place of our application where the dependencies are created. Once our application starts, we prepare our classes for use by configuring them. And during the application runtime, only the methods of our instances are called by each other. So we instantiate classes only in one place, and then we can use the instances. Here's an example of wiring dependencies for a simple script. We parse the command line arguments passed to the program. Once we have a path to a configuration file, we parse it to a dictionary. Then we create dependencies and finally invoke some method of one of our instances. It will work in such a small script, but as the number of our dependencies and connections between them grow, it will no longer be so easy to maintain them in this form. And that's the moment when we need a dependency injection container, which is an object which stores all the dependencies of your application in one place, in one object. There are multiple implementations of containers in several different languages, also in Python. This container is written using open source library called Nut. So first you create the container object, then you register dependencies by decorating functions in which you instantiate your objects. Thanks to the container, we can easily access any of the dependencies. We don't do that in application, but we could, for example, do that in a Python shell. So if I'd like, for example, to retrieve some data from a database, I can go to the shell, create the the container and get the repository instance from the container and call its method to get the offers. We can also write integration tests against dependencies which are already wired together. So for my classes, I write unit tests where only one class is tested at once. All the dependencies are fakes, stubs, or mocks. For my instances, I write integration tests which assert that my final dependencies work well together. If I want to exchange just one dependency for my integration tests, for example, I don't want to send emails from my tests, I can easily register a fake email sender in the container, just for the sake of testing. Here's the continuation of this container, because it didn't fit on one slide. Okay, till now, we talked about classes that perform some actions, about the report formatter, report preparator, and email sender, and their dependencies. But if you look again at this method, you will see that there's one more class here. The instance returned by the report preparator. It's an instance of a report class. It was not injected anywhere. We didn't even have to mention it when preparing our dependencies. So how does this class differ from the rest? We can categorize classes into two different types: services and data structures. There are many different names for them, but let's stick to those today. So services are the classes that we wire together. We can describe them as verbs because they perform some actions. They perform actions on data structures which are passed to their methods as input arguments. They can also return new instances of data structures, like the report preparator returned new instance of the report, but the formatter accepted the report instance as an input argument. Services don't store any data, they are stateless. Data is only their input and output. Examples of services could be the report formatter, email sender, or offers finder. And the other type of classes is a data structure. Data structures are noun for verbs. For example, report, email message, offer, or a user. Data structure's responsibility is to store and represent data. They don't do anything. If you want to do anything with them, you need a service for that. Data structures store the attributes, store the data and attributes. They aggregate data into one object. If we have some data that always goes together, like first name, last name, and email, we don't have to pass all the values as separate function arguments. Then we can aggregate all of them into one class, like this person class, and we can pass one argument instead of three. We pass this instance of the person. Data structures don't have to expose any public method. If they have only attributes, it already helps us a lot. But if they do, the methods should not interact with the outside world. They should not access the global scope. Methods of data structures could be used either to change the object state or to return some values computed from attribute values. So in this example, we have a full name property that returns the person's full name computed from first name and last name. The married method changes the object state. It changes the value of the spouse attribute and optionally last name. If you wanted to send an email to this person, we wouldn't implement send email method, but an email sender class which would accept the person instance as an input argument. And here are some rules for dependency injection. Service objects can be injected into other service objects, but service objects cannot be injected into data objects. It would be irritating to pass an email sender every time we create a new user. Data objects cannot be injected into service objects. Then we would have to create a new service, new instance every time we want to use it. But as our services are stateless, we can create them only once and use this instance to work with any data. Data objects, however, can be injected into other data objects. So we could have, for example, a house with a kitchen, which has a sink and chairs, a table. So in our example, we pass the offers to report. Both of them are data structures. And we pass report instance into the formatter, but we don't inject it into the initializer. Okay, that's it. Now I can only tell you about some of my observations when working with solid principles. First, when I saw them, I thought that my applications would end up with tons of small classes, which would unnecessarily increase the size of my code base. And of course, there are more classes if you keep them small, but from my experience, I can say that it's a lot easier to understand and maintain them than if I had huge classes with mixed responsibilities. And the number of new classes drops in time, because the classes that I wrote once appear to be reused in many different places and contexts later. When I want to write a new class, usually I find out that I already have it, and I can reuse it. On the other hand, if you use functions instead of classes, you have more of them, because they can be reused with different dependencies. Instead, you have lots of small functions with the same logic and the same test, but they have different dependencies hard-coded. In classes, I separate logic from coupling. I found out that it's often easier to understand the class when I can focus only on the logic, and the dependencies do not distract me. As I said before, I write unit tests for classes and integration tests for the instances. Thanks to that, I have a clear separation, and my unit tests are faster and more portable. Because my classes can be used not only inside my application. It happens that a similar functionality that I have in my application is needed in some other project. And as my modules are independent, I can extract them to a third-party library, and other people can use it in other contexts, even if they use another framework or another database. And as my unit tests are separated, I can extract them along with my modules. Not only me, but also my colleagues who are from work who were first skeptical about Solid have observed that when following these principles, it's a lot easier to split history into logical commits with very readable divs. And thanks to this, code reviews are now much quicker, and it's a lot easier to spot bugs or bug design. And last thing, even if you write bad code in one class, because you're tired or in a hurry, it's easy to replace it later with better code, because it's not coupled with the rest of the code. So you change only this class, you write a new one, delete the old one, and everything's good. Okay, that's all. Thank you.
Right, does anybody have questions? Don't be afraid.
I'm already afraid.
Thank you for the great talk. What do you think about using closures to achieve dependency injection with pure functions without classes?
Do you mean, for example, the partial function from context loop? Not context loop, but functools in Python? There's a function called partial, a helper which helps you to create a new function with the dependencies already injected.
Also, I meant closure, just strictly but partial can take the same role.
Well, I don't have any experience with that. I only tried this partial thing, Because I saw this talk, Write Less Classes, I think that's the name of this talk, where the guy said that if you have a class which has two methods, one of which is init, then you should use a function. And he said that when you want to inject dependencies, you can use the partial function. And I tried to do this, but still, as I said, I have the interface polluted of the function because I have both input arguments and the dependencies. Even if I don't have to call them every time, I still have them in the signature, which makes it less readable. And when I try to compose one object from multiple functions using this partial function, I was immediately lost. It was so hard to read when I used this partial thing. So, hope this answers your question.
Firstly, just for the note, closure functions are better known in Python world as nested functions. So usually you call it that way. Closure is more computer science term for similar thing. And my question is, how do you achieve separating applications or modules when you have very complex application? Do you still have one process to set up the structure of the application? It was called container, yeah. Do you still have one big container or multiple smaller ones?
Well, the container is, I think, the only one thing in Solid that I'm not so comfortable with. Because when you have a huge container, it's still not so easy to maintain. You have to give names to all your instances, and you have everything on the same level. So it's not so easy to find a dependency that you're looking for. And I tried to implement my own container, which is, I think, a bit better than the not one that I showed you. And I'd love to see or to implement on my own a container that would be able to be split into modules, as you said, because it would increase readability. So I haven't tried.
I think that they can compose one object using two objects for two parts of the system.
Yes, you could do that.
That's one strategy, I think.
Mm-hmm.
Okay, thanks. If you had such experience, did you try to live with that solid principles inside frameworks which doesn't follow those principles?
Sometimes it's really hard to follow these principles in Python because most of actually pretty all of the open source libraries in Python don't follow them, and they are closed for extension, so it's hard to inject something other than it's hard-coded. So yeah, sometimes it's painful, and you have to write lots of adapters, and sometimes you have to rewrite functions because it's impossible to inject something different. Yeah, that's a problem. That's why I'm giving this talk, because I'd like people to follow them and to open their code for extension.
Okay, unfortunately that's all the time we have for these questions. If you have any more, then contact Ignacy after the talk. And the next talk will be starting in 5 minutes.
Thank you.